Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 40 and we will be looking into traps and defects at cryogenics, but we will start from where we left in our previous lecture, which is lecture number 39. And this is basically your ideal low frequency capacitance versus gate voltage model. We have actually looked into accumulation and we have looked into strong inversion. However, we will now look into moderate inversion and depletion. So, let us look at the moderate inversion part. In the moderate inversion is the place where full inversion has not taken place, primarily meaning that there is no inversion layer as such, but the electrons are getting filled up slowly and slowly as the gate voltage is increasing, and that is the reason your capacitance seems to be increasing, because capacitance depends directly on the charge. If the number of charges becomes much larger, then the capacitance actually increases. If you remember, C equals to, as I discussed with you, dq dV. Now, if this capacitance del q is relatively large, the capacitance increases. Why does it increase? Is because it is in the numerator side, more is the capacitance, more is the charge. Now, as you make the gate voltage go higher and higher incrementally, somewhere near this value in this region, you are adding more and more inversion charges as such. In the strong inversion, there is no further addition of any minority current, in this case electrons in this case. But when you are not in the strong inversion, you are in the moderate inversion region, you will be adding more and more charge carriers here, which are basically electron, and that is the reason you will see that your capacitance tends to increase. So, there is an increase here. Now, let us come to the place where we were talking about the depletion. In the depletion region, which is the blue curve to the left of Vt, solid line, in the depletion region, the left side as you can see, as the gate voltage starts to increase. So, you understand that what is happening in the depletion region, you are depleting all your charge carriers, right. So, there is the effective thickness is going on increasing. When the effective thickness goes on increasing, the capacitance will surely fall down, right. So, what has happened was, initially in the accumulation region you had number of charge carriers were high, you depleted it, so there are no charge carriers. So, the effective thickness goes high and therefore, your overall capacitance goes low, and that is what is happening. If you see, as you therefore go on increasing the gate bias, the capacitance actually starts to fall down because your effective thickness goes on increasing, and therefore, since in the denominator the oxide capacitance goes on increasing. Somewhere around threshold voltage where the inversion sets in, you are now adding reverse type of carriers near the interface, and therefore, the charge carrier again increases, and therefore, the capacitance again increases, and that is the reason you see at the top. So, this is basically a low frequency capacitance. Low frequency means the input signal which I am giving to extract the value of capacitance is of low frequency. So, if you extrapolate this one, this is basically this dotted curve which you see is the extrapolation of the accumulation region, and if you extrapolate it, it should meet with the oxide capacitance in the strong inversion. If you look at this dotted curve here, this is basically your depletion region capacitance is extrapolated backwards. The place where, so if you remember our previous discussion, we had seen that it was 1 by C prime was equals to 1 by C ox plus 1 by C S D prime, right. So, this is the point where you get the C prime. At the threshold voltage, you have the minimum capacitance as such. This is quite interesting. Please keep this in mind, that therefore, at threshold voltage your capacitance, effective capacitance is minimum, goes on increasing as you increase the gate voltage. Now, the flat band voltage or the flat band capacitance is basically occurs, this is the flat band capacitance CFB, this one, this is the flat band capacitance, right, VFB, where it just shifts from accumulation to depletion, and that is given by this expression here, right. I am not going into details of this, and therefore, it primarily depends upon the oxide thickness Tox, and it also depends upon the acceptor semiconductor doping in a sense, which is CFB prime. Right. So, the 4 regions of operations here, let me recapitulate what we did. In a sense, accumulation, depletion, moderate inversion and inversion, 4 regions of operations there for a p-type substrate. Now, I have already discussed, I will not go into details of this, already we have included, but as I told you quickly, we can say moderate inversion lies between strong inversion and the depletion region. Here both the space charge and the inversion layer contribute to the capacitance. In the strong inversion, it is only the inversion charge which contributes, in the depletion it is only the space charge which contributes. Moderate inversion is the place where both it contributes. When you go to strong inversion region, which is the next slide, you will see that due to screening effect, the space charge region does not come into picture at all, right. And this is how we go. So, therefore, typically if we break down the characteristics into 3 parts, then we see that in the accumulation region the capacitance is Cox, and it reduces to depletion width at the depletion region, and in the strong inversion capacitance against approaches Cox prime, right, which is the maximum capacitance in a sense. So, this is how the variation in the capacitance takes place for various regions. Now, let us come to the trap charges, right, because this is quite interesting and important also. Since we have learned the CV, ideal CV, now let us introduce fixed oxide and interface trap charges, and let us bring in non-ideality. We will look into the impact of CV characteristics therefore because of interface trap charges. We look at its application and then charge trapped in the interface states, and then we will look into high frequency. Low frequency does not, by the way, catches the trap charges, but high frequency catches the overall interface state effects in the MOS device. I have already discussed with you what is fixed oxide charge, right. Fixed oxide charge is a charge which is there in the oxide layer, and that tends to change the threshold voltage of the device. Now, if you look at the CV characteristics in a sense, on the right hand side I have applied the CV characteristics, and I am saying that it is basically its accumulation region and then going to the C min region, which is the minimum capacitance region near the threshold. Now, as I discussed with you earlier, when we were discussing ideal MOS, there were no fixed oxide or interface trap charges. The fixed oxide charge is referred to as QSS prime here per unit area, and this causes a shift in the flat band. Why? So, you understand flat band is basically the amount of potential required to make the band flat between the metal and the semiconductor. Now, if there is a fixed oxide charge already available, you require larger amount of voltage in order to flat band, and that is the reason you happen, or a smaller amount depending upon the nature of the oxide trap charges. If you look at the equation here, VFB is given as phi ms minus QSS prime by C oxide, which is basically meaning that larger the value of the fixed oxide charge, lower will be your flat band, which effectively means that if you go on increasing the value of your fixed oxide charges, then what happens is my VFB starts to shift to a lower and lower value. So, the VFB3 corresponds to QSS3. Actually, I can assume this to be as a positive one in order to explain to you this curve at least. What I am trying to say is, as the value of QSS goes on increasing, your flat band voltage also goes on increasing. Why? Because you need to deplete those fixed charges in order to do a flat band, and that is what the reason is. So, if we talk of QSS1, it corresponds to VFB1 here, VFB2 here, and VFB3 here, depending on the value of QSS, right. And if you take QSS ideal, which means that there are no fixed charges, then we have already seen what you will get in that case. In that case, you will be having very low VFB0 will be there, right. This is VFB0, this one, this will be VFB0 in the ideal condition. Now, therefore, parallel shifts in the CV characteristics with respect to oxide charges, there will be fixed oxide charges, there will be parallel shifts in the CV, at least from the accumulation to the depletion region of operation, right. And this parallel shift because of the change in the fixed oxide charges. However, if you look at the overall shape qualitatively, it remains unchanged, right. So, as QSS increases, there will be a progressive shift to the left, as I discussed with you. The VFB starts to increase. VFB starts to increase primarily meaning that you apply larger and larger sort of potential. This is basically high frequency CV. We will discuss this later on, but just for information's sake, this is a high frequency CV. In high frequency CV, this does not go to the top, right. This is low frequency and this is high frequency. So, this is your low frequency which we have already studied in our earlier cases. This is VT. In high frequency, this sort of merges down. So, you remember why in the strong inversion there was increase in the value of the capacitance, because the charges were getting accumulated, getting inverted onto the interface, and beyond a point the whole saturation of the charge took place and the inversion layer capacitance in strong inversion was constant. However, when you go for high frequency, the variation in the gate potential is so strong that the charges will not be able to replicate the changes, right, and therefore the capacitance falls down, and therefore there is no accumulation of charges there, and the capacitance falls down to bare minimum, which is C prime min. So, if you plot sort of CV, let me draw it for you here because it is not there. This is how low frequency looks like, right. For high frequency, up till this much point it remains the same, and then it starts to flatten out here, which is C min prime. minimum capacitance per unit area happens here, and this is the low value which you see here. This is for the low frequency and this is for high frequency, right, and this gives you a brief idea about how this high frequency model changes. Let us come to now the interface. We had discussed about oxide charges. Anything more than that is not required for this level, of course. Interface trap charges, let us look into. There are two types of interface trap charges. One is an acceptor type and another donor type. What are these interface trap charges? Origin, you already know possibly. The silicon dioxide interface, some of them the bonds are not quenched properly and there will be traps available in the bond, and these traps can be of acceptor type and donor type. Typically the acceptor type states appear in the upper half of the band gap. So, you have an intrinsic Fermi level which is EFI here, all your acceptor type are above the intrinsic layer. So, this is your band gap and this is upper layer is all acceptor, lower layer is all donor, right. So, basically it exists in the upper half of the band gap, right. Now, and these are all positive charged. Acceptor states they can accept charge carriers, donor states can donate charge carriers. They generally exist in the lower half or in the lower part of the band gap. They are typically neutral when the Fermi level is above them. So, please understand this important point. So, it is a p-type semiconductor, your Fermi level will be somewhere near the valence band, right. So, if this is your EF which you see, then all these states between the band gap and here will be neutral in nature, right. These will be all neutral and these will be charged. Similarly, if this is an acceptor ion, all below will be neutral and above between conduction band and this will be all charged, right. Now, if the Fermi level, so for acceptor ions, all the charges which are below the Fermi level will be negatively charged for acceptor, and for donor it will be positively charged for the when the Fermi level is below them. So, all the above Fermi level will be all positively charged, and therefore, depending on the gate voltage, the interface state charges varies with gate voltage in a MOS capacitor. And that influences its CV characteristics, right. It influences its CV characteristics to a larger extent, right. Okay. So, let me again give you a brief idea. We have understood acceptor states which accepts charges, donor states which donate charges in a sense. It depend upon the placement of the Fermi level with respect to the conduction and valence band, and therefore, since the Fermi level changes with respect to doping as well as with biases EC and EV, how many number of acceptor and donor and how many number of neutral states are a strong function of the applied gate bias. Now, the CV characteristics will help us in determining the equivalent oxide capacitance in a MOS device. So, if you know what is the value of phi ms and Cox, and then we can calculate the value of the ideal flat band voltage, right. We have already seen it in our previous discussion when we were looking at VFB. It was phi ms minus Q ox by Cox which we were getting, right, and that is what we know as a MOS structure. Now, the experimental flat band is obtained from the measured CV. So, in the measured CV you try to find out that position where the flat band, its corresponding capacitance will be flat band capacitance and the voltage will be VFB. But if you change it, say for example, you change the oxide capacitance charges or interface, the shift will be there in the CV. From there you need to find the value of your fixed value of your charges, right. Now, in reality, the oxide or interface trap charges, once they have been formed, typically do not change with large amount of experiments or external elements. They do not change, they only change in one condition, typically when you are analyzing radiation effects in MOS devices. So, what you do is that when radiation, for example a gamma radiation or an alpha radiation falls onto the biased MOS device, they generate electron hole pairs, and when they generate electron hole pairs because of electric field, they tend to get settled in the oxide or interface trap charges. That changes the flat band and the threshold changes. Not only that, the CV characteristics will also shift. Shift means there will be a parallel shift either to the left or the right, right. There will be no enhancement or decrement in the capacitance because of radiation as such, but there will be a change in the threshold voltage of the CV characteristics. And that is the last point which is mentioned in this slide to a larger extent has been explained to you. Now, let us look at the nature of the charge trapped in the interface states. So, you look at the right hand side curve here, and the first one is for accumulation A and part B is for inversion. So, let us look at the accumulation first. The MOS capacitor is biased in such a manner that the Fermi level lies below the donor interface states, right. the Fermi level lies below the donor interface states, and therefore donor interface trap charges, which is this one, the blue colored one, are all positive donors now, and anything below the Fermi level, as I discussed, are neutral donors. Positive donors means basically they are positively charged in a sense, and therefore a net positive charge is trapped in the interface. These are interface trap charges which are sitting few angstrom near the silicon dioxide interface in a sense, right. So, the positive donor part is what? The positive donor part is near the interface, right. Let us look at the mid gap condition, which is mid gap condition, second one, where the Fermi level just touches the intrinsic Fermi level near the interface trap charges in the interface intrinsic level, and therefore both donor and acceptor interface trap charges are neutral in nature. So, there is no net charge in the interface stage. So, when you had accumulation, you had a net positive charge trapped in the interface. At mid gap, when the Fermi level and intrinsic Fermi levels are all exactly matched to each other, and the Fermi level is again in between EC and EV effective charges, there is no net charge in the interface stage. Let us look at the inversion. Inversion, what will happen? The intrinsic Fermi level will go even below the Fermi level EF, if you remember, and all the states above the Fermi level are negative, right, and therefore they are negatively charged. So, you see these will be effectively negative charged. So, what has happened is, depending on the applied bias which you are giving, the effective charge on the interface goes on changing. It was initially positive, becomes neutral, and becomes negatively charged. These are for charges trapped in the interface states, not for anything else, right. So, please keep that in mind. It is basically the total charge at the interface which is coming into picture. Now, okay, so I do have a high frequency CV, great. So, I will explain to you. So, typically there it was a low frequency, now basically high frequency. High frequency is effectively when the frequency is very large and the charges are not able to sort of follow the applied potential to a larger extent. If you look at the ideal CV, which is this one, it is the high frequency curve considering its ideal. This is the mid gap here, I have a flat band here, and I have a threshold here, and this is my high frequency C min prime, which is coming here. And there are very distinct regions. Accumulation is here, right, and this is threshold. This is again depletion and moderate inversion coming into picture. Let us look at the black line, black dashed line, and this is basically the distorted CV characteristics which we see, right. This is the distorted one with interface states. So, the first one was without interface, now it is interface. Quite interestingly, if you look at the very important fact, with interface states at accumulation, the capacitance effectively falls down, and at interface beyond inversion mid gap it increases. I think you might be knowing why this happens in this case, because effectively the charges get transferred in accumulation, which is positive in nature, to a negative in mid gap. If you see very closely, it is exactly the same as the ideal one, because the net charge is 0, and therefore the mid gap and the distorted exactly remains the same. Whereas, if you move to the inversion charge, since the number of negative charge carriers are more in number, you see your capacitance is actually increasing, the threshold voltage is shifted to the right as compared to an ideal one. The reverse is true for the accumulation case MOS devices. Let us look at the flat band point. In the flat band point, at this voltage, the energy bands are flat, as I discussed with you, and all the interface states are effectively neutral. This case, right, this flat band is what I am talking about. However, I can measure the value of CFB due to the fixed oxide charges can be done. In mid gap, what happens? The Fermi level and the interface is exactly equal to the intrinsic Fermi level, right, and therefore the ideal and the interfaced one all matches with each other. In threshold, if you increase your gate voltage to a larger value, there is an inversion layer which is formed, and the acceptor type interface states becomes negatively charged, and the threshold voltage therefore increases, because now you have to apply a larger gate voltage to invert the channel, and that is the reason it shifts to the right slightly in the case of high frequency CV characteristics. And that is the reason you see that forms to a additional capacitance. Why additional? Because you are adding more and more charge carriers here in this, and therefore that leads to the distortion in the curve, which is the dashed curve here. So, what is the basic difference between an ideal one and high frequency and with interface is that the presence and density of interface trap charges determine the non-ideal condition of the CV characteristics. It also explains to me the nature of the oxide trap charges. If it is above Fermi, it is negative, below Fermi, it is positive for trap charges, at mid gap exactly neutral to each other, and therefore device reliability and overall device characteristics are understood by this CV characteristics. Let us now therefore come to the last part of this lecture, and that how does it influence the cryogenic. We will deal with it in much more detail. This we have already studied, right? This one and this one we just now studied, right? However, with cryogenics, and that's interesting, with interface trap charges at cryogenic, what you effectively see is that the capacitance in the accumulation region falls much faster. It the absolute value of the capacitance in the accumulation region is relatively very small here. However, if you go beyond threshold, it is actually lower than the threshold change due to interface trap charges, right. So, the best one is the ideal one, right, which has got no interface trap charges of 300 Kelvin. Next comes the cryogenic temperature, and the next comes the interface trap charges, which you see. With interface trap charges, the degradation in threshold voltage is the maximum which you expect to see, and that is expected also because you need to invert larger amount of charges in this case, right. So, with this, let me recapitulate what we learned in this lecture series. We learned about CV characteristics we have learned about CV at low frequency and high frequency we studied. We looked at the flat band condition, and then ideal case, and then we added interface and oxide trap charges and saw how my VFB and threshold voltage is changing because of this. Finally, we ended up looking at the cryogenic temperature effect on the threshold voltage in the flat band. I hope you enjoyed it. Till we meet next time. Thank you.